So think about this for a second. If you take a piece of matter, say a brick, an apple, or even a strand of your own hair, and you just keep cutting it in half over and over again, do you eventually reach an absolute end? Or does it just keep going on forever? Welcome to this explainer where we're going to start with that exact 2,000-year-old question because it literally sparked humanity's greatest scientific detective story.
Okay, let's dive right in and decode the invisible building blocks that make up absolutely everything in our universe. Honestly, by the time we wrap up today, you're going to see the physical world around you in a completely different light.
We've got a seriously thrilling expedition ahead of us today. Our agenda covers 1. The quest for the atom, 2. Evolution of atomic models, 3. Inside the atomic nucleus, 4. Mapping the electron shells, 5. Valency and combining capacity, and finally 6. Isotopes, the atomic twins.
Section 1. The quest for the atom.
We can actually fast forward through history, tracing this whole idea back more than 2 millennia. Over in ancient India, the philosopher Acharya Kanada suggested that if you divide matter repeatedly, you eventually hit an invisible, indivisible stage. He called it Parmanu. Right around the same time, in ancient Greece, Leucippus and Democritus proposed a very similar concept, coining the term atomos, which literally just means indivisible. But for centuries, this was really just a cool thought experiment. It wasn't until 1808 that an English school teacher named John Dalton took that ancient philosophy and transformed it into a groundbreaking scientific theory, proposing that atoms are the fundamental, unbreakable building blocks of all matter.
Section 2. Evolution of atomic models. Now, what's so fascinating about this next era is how Dalton's whole idea of a completely indivisible atom was turned totally upside down. This brings us to a massive plot twist in 1911. The scientist Ernest Rutherford and his team set up the now famous gold foil experiment. They aimed a beam of tiny positively charged alpha particles at this incredibly thin sheet of gold. At the time, everybody thought the atom was like a plum pudding, basically a soft sphere of positive charge with little negative electrons just randomly stuck inside it. Based on that, Rutherford fully expected his alpha particles to punch right through the gold foil, kind of like bullets slicing through tissue paper.
But to their absolute shock, while most particles did pass straight through, some were deflected sharply, and a few actually bounced straight back toward the source. Rutherford famously said it was almost as incredible as if you had fired a 15-inch artillery shell at a piece of tissue paper and it came back and hit you. No way, right? Well, this single, wild result was the absolute death of the plum pudding model. It proved the atom wasn't some soft, squishy sphere. It had to have a hard, incredibly dense, positively charged center.
He called this dense little center the nucleus. To truly wrap your head around the scale of this new planetary model of the atom, I want you to imagine the atom as a massive cricket ground or a baseball stadium. If the entire atom is the stadium, the nucleus, which holds nearly all of the actual mass, would be a tiny grain of black pepper sitting right on the center pitch. The rest, almost entirely empty space.
And to blow your mind even further regarding how tiny these atoms actually are, you would need to stack about 1 million of them just to equal the thickness of a single sheet of paper. Seriously, think about that the next time you turn a page in a book.
Section 3. Inside the atomic nucleus.
Let's move to the next step of our mystery and zoom all the way in on that tiny black pepper grain at the center. The crucial point here is that atoms are not indivisible after all. They're actually made of 3 smaller subatomic particles. You've got negatively charged electrons orbiting on the outside, and crammed together inside the nucleus are positively charged protons and neutral particles called neutrons, which, by the way, were discovered a bit later by James Chadwick in 1932.
Think of these particles as the ultimate ID cards for matter. The number of protons alone dictates the element's entire identity. We call this its atomic number. So if you have 6 protons, you're always carbon. End of story. Meanwhile, the heavy protons and neutrons packed together make up almost all of the atom's weight, which we call its mass number. The electrons? They're so ridiculously light that we basically just ignore them when we're weighing the atom.
Section 4. Mapping the electron shells.
But since the nucleus holds all the weight, what are those lightweight electrons doing buzzing around in the rest of that vast empty space? Well, a brilliant physicist named Niels Bohr finally gave us the answer. He figured out that electrons don't just wander randomly around the nucleus like a swarm of angry bees. Instead, they follow strict mathematical rules, living in specific fixed energy shells. He named these shells K, L, M, and N. And there's a really strict occupancy limit here. The maximum number of electrons in any shell follows this neat little formula, 2n squared. More importantly, the very outermost shell can never, ever hold more than 8 electrons.
The way those rules play out in reality is just brilliant. When you map out the first 18 elements, you see the electrons filling up step by step, from the inside out, almost like you're adding layers to an onion. Hydrogen gets 1 electron in the inner ring, helium gets 2, then that ring is full, right? So lithium has to start a whole second ring. It's an incredibly elegant, beautifully ordered system.
Section 5. Valency and combining capacity.
Now you might be wondering, why does this whole onion layer structure even matter? Because understanding these outermost shells is the absolute key to understanding how every single material in the universe interacts. You see, atoms crave stability, and in the atomic world, stability usually means having a perfectly full outer shell, which, for most elements, means having exactly 8 electrons. We call this an octet. An atom's valency is simply its combining capacity. It's the exact number of electrons it needs to trade away, steal, or share with its neighbors to hit that magic, stable number. This incredibly simple rule of 8 is exactly why water forms, why metal rusts, and why the cells in your body can bond together to keep you alive.
Section 6. Isotopes, the atomic twins.
As we near the end of our explainer, we really have to look at a fascinating anomaly that scientists uncovered once they finally got to grips with the nucleus. Sometimes, atoms of the exact same element are born as twins or even triplets. Take carbon, for example. To be carbon, an atom absolutely must have 6 protons. That is non-negotiable. But nature occasionally packs a little extra neutral weight into the nucleus. So you end up with carbon-12 with 6 neutrons, carbon-13 with 7, and carbon-14 with 8. They behave exactly the same chemically, but they carry different amounts of heavy neutrons. We call these atomic twins isotopes.
And this beautifully clears up something you might have noticed in chemistry class. It explains why atomic masses on the periodic table are so often messy fractions. Chlorine, for instance, exists in nature as a mix. About 75% is chlorine-35 and 25% is the heavier chlorine-37. When you calculate the weighted average of these two isotopes, based on how often they actually occur on Earth, you get an average atomic mass of exactly 35.5. Mystery solved, right?
But these atomic twins aren't just fun trivia. They are extraordinarily useful in the real world. Because some isotopes are heavier and slightly unstable, they emit radiation that we can actually harness. Uranium-235 is the heavy-lifting fuel powering nuclear reactors. Cobalt-60 and iodine-131 provide life-saving, highly targeted radiation treatments for cancer. And carbon-14? It acts like nature's own stopwatch, allowing archaeologists to figure out the exact age of ancient fossils and human artifacts.
In fact, entire scientific institutions are dedicated to harnessing this incredible power. Cutting-edge facilities, like the Baba A Atomic Research Center, rely on these deep atomic insights every single day. They manipulate atoms and isotopes to develop new medicines, design advanced superconductors, and pioneer the clean energy solutions that are going to power our future. What started out as just a philosophical debate in ancient Greece and India has literally become the engine driving modern society.
We've clearly come a long, long way from the days of ancient philosophy. We've cracked open the uncuttable particle, found the dense nucleus, mapped out the electron shells, and learned to harness the sheer power of isotopes. But as you look at everything around you today, the screen you're watching, the air you're breathing, the very hands you're using, ask yourself, is this quest truly over? With the dizzying, unpredictable world of quantum mechanics still unfolding, are there even deeper, stranger atomic mysteries just waiting to be solved? Thanks so much for joining me on this explainer, and remember to always keep questioning the universe around you.